You know that little zap you get from a doorknob? We've all been there. But what if I told you that pretty much everything we call static electricity is, well, wrong? Starting with the name itself. Let's find out what's really going on.
Oh yeah, you know the feeling. You're shuffling across a carpet, you reach for a metal doorknob and zap. That tiny spark is a universal experience, this little mystery we all share. And today, we're gonna crack it wide open. And here's the real kicker. The reason for that zap isn't what most of us were ever taught. The very term we use, static electricity, is fundamentally misleading. It actually sets us off on the wrong path from the very beginning. So let's start by breaking down that name. Why is it such a problem? And more importantly, what should we be calling it instead? Okay, so here's the core issue. The term static electricity implies that there's some special kind of electricity that just sits still. But electricity, at its heart, is all about the movement of charge. So that word static, that's where all the confusion really begins. The correct scientific term is electrostatics. Now, it's not the study of static electricity, but the study of electric charges that are static or at rest. And that's the key difference. The charges are stationary, not the electricity itself. Okay, so we fixed the name. But what about the cause? Most of us learned that you have to rub things together, your socks on the carpet, to create this effect. But is that really what's happening? And here's myth number 2. The idea that friction creates charge? Nope. Charge can't be created or destroyed, it can only be moved around. The reality is that simple contact between two different surfaces is all it takes for the process to begin. The rubbing just increases the amount of contact and, amps up the energy involved. So here's what's really going down. When two materials just touch, that contact generates enough energy for some electrons to literally jump ship from one surface to the other. And just like that, an imbalance is created. One surface now has a small surplus of electrons and the other has a small deficit. And this right here brings us to the real key, an imbalance of charge. It's this concept that completely replaces that old, flawed idea of a buildup. It's really easy to imagine a huge pile of extra electrons gathering on a surface, but that's not it at all. The reality is much more subtle. An object is considered charged when it simply has a slight imbalance, just a few more or a few less electrons than it has protons. That's it. And this leads to another common misconception. A neutral object, like that doorknob, isn't empty of charge. No way. It's packed with trillions of positive protons and negative electrons. The key is that they are perfectly, beautifully balanced. And have you ever wondered why scientists chose the names positive and negative? They could have picked anything, right? Black and white, up and down. They chose these terms because, just like in math, when you combine an equal amount of each, the net effect is zero. It's an incredibly simple but powerful idea. It's also so important to know that charge isn't some smooth fluid. It's quantized. This just means it only exists in tiny, identical packets. The smallest possible packet is the charge of a single electron. So any charge you ever find is always a whole number multiple of that amount. You can have the charge of 10 electrons, or 1,000,000, but you will never find the charge of 2.5. So we have this charge imbalance, and as we know, it creates forces, attraction and repulsion. But the rules aren't always as simple as opposites attract, which, you guessed it, leads to a fun little puzzle. So think about it. You rub a balloon on your hair, giving it a negative charge imbalance. Then you bring it near a neutral wall, and it sticks. But wait a minute, the wall is neutral, not positively charged. So how can it attract the balloon? What's going on here? The answer is a beautiful process called polarization. The negatively charged balloon actually repels the electrons in the wall's surface, pushing them slightly away. This leaves the positive parts of the atoms, the nuclei, slightly closer to the balloon. And since the attraction to the closer positive charges is stronger than the repulsion from the farther negative charges, the balloon sticks. This is why physicists are so precise. The old rule isn't wrong, it's just incomplete. Adding the word point is critical. For tiny, point-like charges, the rule holds perfectly. But for larger objects like a balloon and a wall, the story gets way more interesting because of polarization. Okay, we've deconstructed the name, we've busted the myths about the cause, and we've explored the forces. Now let's bring it all together and finally solve the mystery of that doorknob shock. So when you shuffle your feet on the carpet, electrons jump from the carpet to you, giving your whole body a slight negative charge imbalance.
That metal doorknob is neutral, and it's a great conductor. As your hand gets close, that imbalance becomes so great that electrons literally leap across the air gap to the doorknob to restore balance. That sudden flow of charge is the current you feel and the spark you see.
So, let's recap the fundamental rules of charge we've uncovered. First, it's quantized. It comes in discrete packets. Second, it's conserved. It can't be created or destroyed, only moved. Third, it's always associated with mass. And finally, it's invariant. An electron's charge is the same whether it's sitting still or moving near the speed of light. These are the core principles of electrostatics.
We've explored the fascinating world of charges that are static. We understand the forces and interactions they create, but this all leads to an even bigger question. What happens when these charges are no longer at rest, but are flowing in a great, steady river? Well, that is a story for another time.